Hello students, welcome to next lecture. In this session we will be discussing voltage control of single phase inverters. So voltage control, why is it required? So in industrial applications, the control of the output voltage of inverters, we know that inverters are those which convert fixed DC to variable AC output voltage, right? So in most of the applications, the inverters are required to perform in such a way that it has to cope the variation in the DC input voltage. Okay, so even when there is variation in the input DC voltage, it has to give a proper controlled AC output. It has to provide the regulated output, and the inverter also should satisfy the alter frequency control. Okay, say for example, as I mentioned here in the slide, um, if a load demands fixed AC output, then the inverter must be able to provide fixed AC voltage, right? So there the voltage control comes into picture. That is, a voltage control from the inverter has to be done so that it will be able to provide fixed AC voltage even when, say, if there is any variation in the input DC voltage. All right. Also, in a situation where if the inverter supplies induction motor, where for induction motor we know that the voltage per voltage frequency, that is voltage to frequency ratio, has to be maintained constant for at the motor terminals, right? So even at this situation, the inverter should be able to provide this constant voltage and frequency ratio. So in these situations, the voltage control comes into picture in inverters. So there are different methods to control the voltage. First is external control, wherein the AC output voltage or the DC input voltage will be externally controlled. Externally controlled means here the inverter circuit as such will not be disturbed, but there will be additional converter stages that can be included in the say before the inverter or after the inverter, depending on whether you are controlling the DC input voltage or AC output voltage, right? So other method is internal control. In internal control, as I mentioned, the inverter circuit itself will be altered or varied or say modulated in order to provide the voltage control. So the control of the output voltage is within the inverter here. All right. So externally controlling the AC output voltage, there are again three methods. Two methods: AC voltage control and series inverter. This is a typical simple block diagram of AC voltage control. As you can observe here, you have the constant DC voltage. Okay, AC voltage control means obviously you're controlling the output voltage, right? So you have the DC voltage, constant DC voltage, which is fed to the inverter. So the output of the inverter can be fed to AC voltage controller, right? So we know AC voltage controller is the one which will be controlling the AC voltage to regulated or fixed variable output, right? So the output what you will be getting from AC voltage controller will be the controlled AC voltage. So that can be fed to the load according to the application. So as you can see, the output of the inverter is controlled, the output voltage is controlled by using another setup or the additional circuitry here. The additional circuitry is here, the AC voltage controller, right? So it's a generalized block diagram as such. So maybe you have to include all the discussions what we had in previous sessions, right? So externally controlling the DC input voltage, look at the block diagram. again, this is a generalized block diagram here. Say if you are controlling the DC input voltage of the inverter, observe the blocks here. Say you have AC voltage, right? That AC voltage you are feeding it to fully controlled rectifier. Rectifier circuit, that is control rectifier, you know, you have power semiconductor devices there, wherein controlling the firing angle, you can control the output, right? So you'll be getting controlled rectifier output, which will be a pulsating DC, right? So this pulsating DC can be fed to the filter to remove the AC components there, and you will be getting the controlled DC output, DC voltage, right? So this will be like fixed or say controlled DC input that you can use it for your inverter circuit. So as you can observe here, all these are externally controlled. So you are not disturbing the inverter circuit as such in both the cases, but you are externally adding the additional components either before or after the inverter circuit, right? So today's topic is what we are discussing is the voltage control, which is internal control. So internal control, which is very important, as I mentioned earlier, wherein the inverter circuit will be adjusted or modulated or changed to have this voltage control. Okay, so the most popular method is using pulse width modulation technique. Pulse width techniques, modulation techniques are characterized by the constant amplitude pulses, wherein the width of the pulses will be varied or modulated in order to get the required output voltage. Okay. Yeah. So the width of the pulses in pulse width modulation technique will be modulated in order to get the desired inverter output. Okay, and this method is also used to reduce the harmonic content in the output voltage. So we will be discussing how it will be done here. So there are again three types in pulse width modulation technique. First is a single pulse modulation. Second, multiple pulse width modulation technique. Then third is sinusoidal pulse width modulation. Then again there are fourth and fifth wherein you have modified sinusoidal pulse width modulation and phase displacement control. So in this session we will be only discussing single pulse width modulation technique. So again, this is a generalized block diagram of single pulse width modulation technique. So there is a comparator here and there is a trigger pulse generator which will be generating pulses to trigger the semiconductor devices, that is SCRs, in your inverter circuit. So the input to the comparator, as you can see, there is a carrier wave and the reference wave. So generally the carrier wave is a triangular wave. So the frequency of this reference wave, which will be generally square wave, the frequency of the reference signal sets the output frequency. Okay, and the carrier frequency determines the number of pulses per half cycle. So based on the carrier wave and the reference wave, the comparator will be generating whether the low or high output. So which will be triggering the pulse generator to generate the pulses. So these pulses will be say turning on or firing the SCR devices. Okay. So let us observe how it works. Here is the simple waveform of the working of this single pulse modulation technique. As you can see, the triangular wave, what you can see here is your carrier signal, and the square wave, what you see is the reference signal. So carrier signal is represented as VC here, and the reference signal is VR. So whenever VC is less than VR, whenever the value of VC signal is less than VR, say for this duration, as you can observe here, um, then the comparator output will be low. So there will be no output from the comparator. So there will be no pulses from the pulse generator. Okay. Now, whenever the carrier signal VC is greater than the reference voltage, as you can observe here, between this duration, then the comparator output will be high, causing or giving a signal to the pulse generator to generate the pulse. Okay, so the pulse generator will be generating the pulse depending on the value of Vc till it is greater than Vr. Now, as you can observe here, Vc is crossing Vr, is greater than Vr from this duration till here, right? So once it becomes less than Vr, that is when again comparator output will be low and the pulse generator will stop generating the pulse. So this will be generating the pulses of, say, fixed amplitude ETC. As you can observe here, the amplitude will be always fixed ETC, but the duration is controlled by this, or it depends on the value of the carrier signal and the reference, obviously, and the reference signal. So whenever Vc is greater than Vr, so for that duration you will be getting the pulse generated by the pulse generator according to this generalized block diagram. So this pulses will be given to the semiconductor devices which will be conducting or turned on. So whenever they are turned on, we obviously know that there is the output, right? So this is the waveform what you can observe here. The output EDC is represented as VL, or you can also take it as V naught. Okay. So the output what you will be getting will be the amplitude will be EDC, and the duration it depends on again the VC and VR. So the output what you can observe here, it is called the modulated output. Okay, it is also called quasi square wave. It is quasi square wave because, say, from this duration to this duration the output is 0, and here during this duration it is non-zero, during this duration it is 0, and during this duration it is non-zero. So it is a quasi square wave. So again, even in the negative cycle, I hope you are able to recall it. Say for example, if you consider a single phase full bridge inverter, that is bridge inverter. So you will have 4 switches there, S1, S2, S3, S4, or you can also take it as T1, T2, T3, T4. So you have to T1 and T2 will be conducting in the positive cycle, and T3 and T4 will be conducting in the negative cycle, right? So to turn on T3 and T4, this negative part, that is whenever Vc is greater than Vr, a pulse will be generated which will be equal to minus EDC, as you can observe here from the waveform. So it is similar to the output what we had discussed in the previous class. This is the output voltage without modulation. Sorry, it has to be without modulation. So we saw that it was between 0 to t by 2 and t by 2 to t, right? So the output was plus EDC or minus EDC, yeah, a square wave. But here with the modulated output, you can see, observe the difference there. The output what you will be getting will be quasi square wave. Okay, so yes. So the Fourier series of this square wave, we have already discussed in the previous class. It is given by, you can write the Fourier series using this expression where VL is equal to, VL is nothing but your V naught is equal to A naught plus summation n is equal to 1 to infinity A n cos n omega t plus B n sin n omega t, right? So where A naught is your average value, right? Average value for square wave it will be 0 because it is a symmetric signal or the wave. So average value will be 0. And you know, we have already discussed that the an component for the square wave will be 0, and bn we observed that we got it that 2 by pi 0 to pi edc sine n omega t d omega t. So sine n for all values of n even numbers will be equal to 0, and we got that for n is equal to odd numbers the output was 4 edc by n pi. This we have already discussed, you can refer the previous sessions. Okay, so we saw that for this particular unmodulated output, we saw the output has only odd components there, right? For all odd components, that is from n 1 3 5 to infinity. So it was given by you can substitute vl is equal to summation for all values of n odd numbers 4 edc n pi into sine n omega, right? So for this quasi square wave, that is the today's discussion for this output. This output, let us observe how we can derive the Fourier series and also the RMS output voltage. Now, to find the RMS value expression for the quasi square wave, let us go to the waveform again. Okay, yeah. So here, as you can see, during this period, that is, you are getting the output from this time instant to here, right? So this point is nothing but pi by 2 minus delta by 2. Say if the width of the pulse is delta, okay, and this the center is here pi by 2, so then this part of the pulse will be pi by delta by 2, right? And the remaining will be again delta by 2. So this point will be, this point where my arrow is, this point will be pi by 2 minus delta by 2, right? So this point where the mouse is placed, so it will be pi by 2 plus delta by 2, right? Similarly here, for this duration, here it is 3 pi by 2. Okay, so if the center is 3 pi by 2, again as I mentioned here, if the width of the pulse is delta, then this part will be delta by 2. Okay, and again this part will be delta by 2. So this instant will be, this time instant omega t will be pi 3 pi by 2 minus delta by 2, and here it will be 3 pi by 2 plus delta by 2. I hope you are able to get my point. So if you observe the waveform, the limits what you have to take, the output what you are getting here will be from pi by 2 minus delta by 2 to pi by 2 plus delta by 2, and here 3 pi by 2 minus delta by 2 to 3 pi by 2 plus delta by 2, delta by 2. Okay, we'll go back to the expression here. Yes, so the output voltage, RMS value of the output voltage, we can take it as, say for one cycle, that is 1 by 2 pi. So the first part of the output what you have there, so from pi by 2 minus delta by 2 to pi by 2 plus delta by 2, the output is plus edc, that is square d omega t, plus the second part, that is where you have negative minus edc, so taking square it will be plus, right? So the limits will be 3 by 2, 3 pi by 2 minus delta by 2 to 3 pi by 2 plus delta by 2. So EDC square, because it is a, even though it is negative, when you take square it will be EDC square, all under square root, right? It is RMS value what you are talking about. So taking EDC square by 2 pi outside the root sign, so you will have EDC by root of 2 pi. So applying the limits, you will get delta by plus delta within the square root. Okay, so finally you will have here 2 delta. So when you will get EDC into root of delta by pi. So this is your RMS output voltage of this modulated wave. So if you observe here, the RMS value of the output voltage, it depends on the delta. As you vary the delta, the RMS value also will vary. So it is related proportionally, right? So the output depends on the width of the pulse, correct? Now let us go to derive the Fourier series of the modulated wave. Okay, so from the waveform again, since it is a periodic signal, as you can observe, and it is a symmetric again. So the average value will be 0. And if you observe here, is this a signal odd or even signal? Observe here, it is a periodic, right? So even you will be getting output here at the before the 0, it will be minus EDC, right? So it will be repeating. So it is a odd signal. So the A naught, that is average value, will be 0. And from this Fourier series conclusion, we know that for odd signal, AN will be equal to 0. Okay, and to find the BN component, okay, let us see BN. We will take it for again one complete cycle, 2 by 2 pi, one complete period. Okay, again within the limits pi by 2 minus delta by 2 to pi by 2 plus delta by 2 EDC sine n omega t d omega t plus the second part of the waveform 3 pi by 2 minus delta by 2 to 3 pi by 2 plus delta by 2 delta by 2 minus EDC sine n omega t. Yeah, so here we know that for all value n even values of n, the Bn will be equal to 0. Okay, so applying the limits here, you will get Bn is equal to 4 EDC by n pi into sine n delta by 2. So this output again, as you can observe, you have this output only for odd values of n, right? Again, the Bn component, okay, the final Fourier expression will be VL is equal to, we know this will be only, will have only the Bn part, right? An will be 0. So this is your Bn part. So what you write here is VL is equal to summation n is equal to 1 to 3 up to infinity, that is for all odd n numbers. So 4 EDC by n pi sine n delta by 2 sine n omega t. This is your final Fourier series expression. So now again, if you observe here, the output, it again depends on the delta. Okay. Now let us observe. I had mentioned in the previous, initially in the initial class that this pulse width modulation technique helps us to remove or reduce the harmonic content in the output voltage. Okay, so say for example you have the nth harmonic component given by VL and M, that is for n component the output voltage VL or V naught, you can take it as V naught also, no problem. So for n component its magnitude, okay, it is given by 4 EDC by n pi sine n delta by 2. Okay, so what if I have to say remove the third harmonic in the output voltage? So what do I have to do in this expression? I have to substitute n is equal to 3, right? So the third harmonic component, the magnitude will be equal to 4 EDC by 3 pi sine 3 delta by 2, isn't it? Wherever n is there, we have to substitute 3. Okay. Now, if I have to remove this third harmonic component, then what has to be done? We know that Sine pi is equal to 0, isn't it? So that means sine 3 delta by 2 should be equal to pi. Does that make sense? So okay, so for sine n delta by 2 to be 0, okay, now we want to know what should be the delta, isn't it, to remove the third harmonic. We know that sine pi is equal to 0, then that 3 delta by 2, that is this part, 3 delta by 2 should be equal to pi, isn't it? Or in other words, it should be equal to 180 degrees. So 3 delta by 2 should be equal to 180, from which we will get delta is equal to 2 into 180 by 3, which will be equal to 120. So if we select delta is equal to 120, then in the output the third harmonic will be absent. Okay. Now observe here. So this part sine n delta by 2. Okay, in terms of sine, in place of, let us go back to the series here. Yeah, sine n delta by 2. Here for different harmonic, whichever harmonic component you want to remove, then this part sine n delta by 2 should be equal to 0, should be made equal to 0. So from that we will be getting, we can find out what should be the delta, isn't it? Say for example, from the waveform now, what should be delta? That is, if delta is equal to 120 means what? Let us go back to the waveform here. Yeah, if this delta should be equal to 120 means what? At this instant, what is this instant? That is omega t is equal to 30. You have to turn on the pulse, okay, and at omega t is equal to 150, you have to turn off the pulse, isn't it? Observe here, pi by 2 minus delta by 2. If delta is 120, according to our expression what we have just discussed, if delta is equal to 120, then pi by 2 by delta by 2 will be what? 30, isn't it? 90 minus 60. 90 minus 60 will be 30. So omega, at omega t is equal to 30, you have to start giving the pulse, alright? And delta by 2 plus, sorry, pi by 2 plus delta by 2, that is 90 plus 60, which will be 150. So omega t is equal to 150, that is when you have to turn off your pulse, okay, wherein the semiconductor devices will be turned on from omega t is equal to 30 to 150. That will be giving you delta is equal to 120. So in turn it will be like you are removing the third harmonic component from your output voltage. I hope you are able to get that. So that is what is explained here. So if you turn on the switches at omega t is equal to 30, that is pi by 2 minus delta by 2, that is 90 minus 60, and turn off at omega t is equal to 150. 90 plus 60, that is the meaning you have delta is equal to 120. So say I want, similarly if I have to remove some other component, say 5, I have to remove fifth harmonic component, then sine phi delta by 2 should be equal to 0, isn't it? So which also means that phi into delta by 2 will be equal to 180, from which delta is equal to 2 into 180 by 5. So which is nothing but 360 by 5. So delta will be equal to 72. So to remove the fifth harmonic component, you have to keep delta, that is the width of the pulse, to be 72 degrees, right? So from this, we can generalize the things. So to remove the nth harmonic component, n delta by 2 should be equal to 120, from which delta should be equal to 360 by n. So for any harmonic component, whichever you want to remove, the delta should be maintained at 360 by n degrees. Okay, so that will be removing the particular harmonic component from the output voltage. Now go back to the waveforms here. Now if you observe, this is your modulated output, and this is your unmodulated output, right? So in unmodulated output, we had already discussed in the previous session that it includes all n odd harmonic components in this, right? All n odd harmonic components are there, that is n starting from n is equal to 1 3 5 to infinity. But here if you observe here, depending on the delta value, this output will always have one value less, one harmonic component less compared to this. You agree with that? Yes. So this output, the modulated output always will have one harmonic component less compared to the unmodulated output. So which means the modulated output is closer to the sinusoidal waveform. Sinusoidal waveform. So that's why this method or this output single pulse modulation technique is used to control the output voltage, and as we have discussed now, it is also used to remove the harmonic content in the output signal. Okay. That is about the single pulse width modulation technique. I hope it is clear. Go through. If you have any doubt, you can always get back. See you in the next session.